Good morning, good afternoon, and good evening to all panelists and delegates from America, Europe, and Indian subcontinent. I welcome you all in today's discussion on technology intervention in areas of clean energy and petrochemicals. I hope that today's discussion will be very much exciting and fruitful and keep you thoroughly engaged. Just to set up the context for today's deliberation, I want to share some data points and my initial thoughts with you on the subject. We know very well India is the third largest consumer of energy in the world. It is the fastest growing major economy in the world. As per IEA, India will account for nearly 1/4 of global energy demand growth from 2019 till 2040, which is the largest for any country. Its share in the growth in renewable energy is the second largest, just behind China. India's energy transition policy is built on four major pillars, that is energy security, that is to reduce in import dependency, energy sustainability, that is to provide the clean energy affordability, that is to make energy affordable to all, and energy accessibility, that is energy available to all. That puts in the center stage of the energy landscape. As per the latest special report on India Energy Outlook 2021 by IEA, India's current primary requirement shall increase from current 929 million ton of oil equivalent to 1573 million ton of equivalent by 2040. The oil demand is also expected to grow in the stated policy scenario to reach 8.7 million barrel per day, that is almost equal to 435 million metric ton per annum by 2040 over the next 2 decades. That is the rise by almost 4 million barrels per day. This is despite the shift of over 60 million ton equivalent in demand due to advent of electric vehicles and increase in share of gas, which India is supposed to increase from 6% to 15%. Energy demand for road transport is projected to move more than double, largely as a result of addition of roughly 170 million passenger car and 25 million trucks between 2019 and 2040. Part of the requirement will also emanate from increased production of petrochemicals as newer refineries are being built with high degree of integration with petrochemicals to reduce the imports as well as meet their ever-growing demand. The petrochemical demand shall increase from current 0.9 million barrel per day to roughly 1.8 million barrel per day. However, India is presently major importer of energy as it imports roughly 85% of oil, 50% of the gas, and roughly 25% of the coal requirement. Thus, India faces formidable challenge to meet their growing demand for sustainable growth, at the same time meeting its commitment to reduce its carbon intensity, CO2 emission intensity per GDP by 30 to 35% by the year 2030 from the base level of 2005. India's import of petrochemical stands at a staggering rupees 94,000 crore for the year 2019-20, which is equivalent to roughly $13 billion. Still, its polymer base is hardly 12 kg per capita against the world average of 35 and the developed country like US, which is around 95 to 100 level. The demand of polymer is going to go up with improving standard of living and urbanization. To put it right perspective, India need almost one cracker of world-class capacity every year for the next 10 years just to meet the demand of polymers. The thrust of decarbonization aided by technological advancement, particularly due to falling cost of renewable power, is likely to result in progressively shift towards electric, LNG, and green hydrogen. India has taken various policy measures and reforms supported by political commitment towards desired energy transition. Now, coming to today's deliberation, we have three very important and very interesting presentations which are relevant topics. The first is titled Crude to Chemicals from Mr. Rama Rao, Director of FCC and Olefins, Llamas, USA. The second one, which is lined up, very interesting and today's hot topic, that is green hydrogen from Mr. JP Soni, Head Process and System Designs, TKLS. And the third one is on forming and handling of carbon rich residue stream from bottom of the barrel upgrading process from Mrs. IPCO, which will be presented by Mr. Marvin Petit. I suggest that we may hold the question and answer session after end of all the presentations. Now, friends, crude to chemicals is a buzzword today. It is different for different countries, considering the domestic feedstock availability, demand pattern, and trade-off between the transport fuel and the petrochemicals. So, first I would like to begin with Mr. Rama Rao, Director of FCC and Olefins, Llamas, USA, and request him to present his paper on crude to chemicals. Mr. Rama Rao, please.
Mr. Rama Rao, you're on mute.
Okay, so do you see my presentation?
Yes, but if you can make it in the
Yes,
presentation slide format, it will be better. Can you make it bigger?
Yeah, 1 minute.
Okay, or otherwise you carry on.
Yeah.
Yes.
So is that looking better?
Yes, it's better.
Okay. Yeah.
yes, sir, this is better.
So yeah, thank you, Mr. Jain, for the nice introduction. My name is Rama Rao Marri. Hope you all can hear me okay?
Yes. You
Yeah.
are audible.
Okay. Yeah. So I'll be talking on the technologies for shifting the fuel-focused oil refineries into chemical hubs. This presentation is co-authored by my colleagues Dan Gillis and Rajesh Summers, along with me. Just before I go into my presentation, I would like to just take a moment to briefly provide the background on the Llamas technology where I belong to. Llamas technology is a global leader in developing the technologies and also implementing worldwide. This Llamas technology has been formed in 1907, which is basically having a legacy of 110 years in the licensing business. This company has been recently acquired by Chatterjee Group and Drone Capital in 2020. And Lummus is the licensor of the petrochemical, refining, gasification, and gas processing technologies. So the portfolio also involves supply of associated catalysts and proprietary equipment and related services. The company has about 3,400 active patents, providing technologies right from the crude processing to the petrochemicals, ranging about 130 technologies, and we have about 2,400 plus licensed units around the world. On the right that you see is the flow scheme that indicates the presence of Llamas everywhere, starting from the crude processing until the petrochemical production. So the theme is basically the managing the current challenges. As the previous session and speakers spoken out very well, it's clear that we need to shift from transportation fuels to the high value chemicals to sustain with the market pressures. The first thing that we noted over the years is the projected demand is reducing for production transportation fuels. That is mainly caused by the electrical vehicles that are gaining momentum. Therefore, to sustain and make still profits, the refineries have to repurpose their assets to produce less fuel and higher yield of the petrochemicals, in the sense that we have to move towards making the lightest molecules. On the other hand, the rising global middle class and increased consumerism is basically also demanding the growth for the olefins, aromatics, and polymer resins that Mr. Jain introduced as a part of this session. So then there are a few other factors like government mandates, which also like influence the profitability of the refinery, because the mandates such as low sulfur gasoline and the IMO ruling on the bunker fuels, asking for very low sulfur, all these will have the significant influence on the capital investment to adhere these requirements. Therefore, bottom line is the shrinking refinery margins. So therefore, it is important to basically move towards producing the chemicals from the crude that will help to enhance the profitability of an existing refinery complex. However, the challenge is to convert incremental drop of the oil into the high value chemicals. So there are various issues that we need to take into account. So the question of refining and petrochemical integration basically has to be seen in a synergy, because we have to repurpose the existing refinery assets to provide the petrochemicals that are high value for the refiners. So the great integration doesn't mean that it is a co-location. It has got a lot of things that to be taken into account, such as low cost feedstock, lower transportation costs for the feedstocks, fuel sources, and existing infrastructure, and downstream markets like polyethylene, polypropylene, etc. And also associated with the complementing refining and petrochemical integration of exchanging the molecules for reprocessing, and also like providing some opportunity to share the utilities that are required. There are two anchors, oil to chemical projects, that it is known now with a lot of publications and a lot of leading conference discussions. One is the carbon rejection, other is the hydrogen addition. So carbon rejection means it is mostly the FCC that has to be there as a secondary processing, which you are seeing on the left side. The feed that is prepared from the crude unit, right from the HVGO to the naphtha to the atmospheric tower bottoms, including treating of some residues and processing the coker oils either directly or hydrotreated, making into all light olefins. And the other anchor for petrochemicals is the mixed feed steam cracker, which is essentially getting the feedstock from most of the hydroprocessing routes. So these two processes are going to play a big role for producing the petrochemical building blocks of the future. It is very important to have a deeper understanding of the molecules. Now, earlier we used to talk the range of the products like gasoline and diesel boiling ranges. Now we are talking the refinery and petrochemical complex in terms of the molecules, small molecules in particular, like starting from the C2 to C4, and also the naphtha or PII. The naphtha means it is BTX-rich naphtha that I'm referencing to. So, like many of the processes are licensed by Llamas technology in this domain as well. The other important consideration is the feed. Which is a crude source and type. All crudes are not equal to be processed as a source of the petrochemical production, because the paraffinic and light crudes are preferred, and the access and sustained light crude availability for a long time is very, very important aspect to be considered for profitable margins continuously. And there is also like an important aspect that regional crude and product pricing mechanism and logistics is another aspect that has to be taken into account. As regards to the impurities, when we process these crudes, the impurities such as constant carbon, metals, sulfur, nitrogen, these are going to play a big role on the profitability of the refinery and petrochemical complex. So therefore, it is important to effectively deal with these impurities. And also, we need to have efficient dealing of the bottom of the barrel, because whatever crude source that we have, depending on the type, we may have the primary conversion or separation to the tune of 30 to 60%. Then remaining has to be upgraded into these light molecules. That makes big challenge to make it more profitable. So the next slide is showing the process configuration, which is aiming to convert the fuel refinery into the chemical hub. As you see, the boxes that are shown here in the gray are the traditional refinery configuration. And the boxes shown in green and blue and orange are basically showing up the new additions to integrate the existing refinery into petrochemical complex. And finally, integration with the derivatives to produce the finished products as chemicals. So this slide is basically a recap of what we have seen in the previous slide, where the refining complex is typically associated with two types of secondary processing. One is the hydrocracking, hydroprocessing, other is the FCC. And there is another important aspect that is also is considered is the residue conversion approach, depending on the type of the crude and the byproduct values and synergies between these processes. So it is important to consider some residue conversion approaches to make the refinery integration to petrochemicals more attractive. Then on the right side, you are seeing the petrochemical additions. As we saw in the previous slide, the light olefins FCC and mixed packers are the anchors that are essential to produce these light molecules, to produce the chemicals. That includes the feed preparation for these two units. And as we are talking the large range of the molecules as a feed, and there will be some molecules that are generated intermediates, and there could be some waste streams. It's important to see for monetizing these co-products, which are byproducts that are produced using the process that are going to complement with the refinery and petrochemical complex. One of such processes is the olefin conversion technology, where it uses the C2 to C4, C2 and C4 light olefins in a metathesis reaction mechanism to produce higher amount of the propylene, an example. And aromatics, like definitely the steam cracker as well as the FCC, both are going to produce a significant amount of the aromatic rich naphtha, consisting of the benzene, toluene, xylene as a rich material. However, the scheme looks really simple, but when we are talking of switching a refinery from a traditional fuel center to the petrochemicals, it requires a thorough understanding and analysis, because there are several variables and the parameters that require careful analysis to make it a profitable solution for long term of a petrochemical and refinery complex. So this is again showing the schematics of a refining complex integrated with the petrochemicals. As you see, the residue upgrading is fundamental consideration for the crude to chemicals. As I mentioned, whatever crude that we get, no matter what we do, there is a significant amount of the residue that is still available, and that needs to be upgraded. So therefore, the secondary processing and upgrading all those heavy molecules into the suitable feed, either into the FCC or into the steam cracker, is going to become an important activity that makes the things lucrative for the refiners. So there are a couple of options here for upgrading the vacuum residue into the light olefins. This includes the LC fining, coking, LC max, several things, ranging the conversion from 85 to 98. The other route that we were talking about is the carbon rejection, where the ultra high light olefins FCC is involved. Llamas is one of the leading licenses in FCC technology, and in high olefins FCC technology in particular. We have about 70 units licensed around the world. We have active R&D with the state of the pilot plants. We have a joint collaboration with IOCL R&D, the technology partnership for the INMAX FCC. Many of you may be knowing the INMAX FCC is originally developed by IOCL R&D, and we, Llamas, collaborate with them for global licensing as well as designing and engineering support. So the IOCL R&D brings in the innovative INMAX catalyst that is developed indigenously, along with the process concepts that are employed in the FCC technology offered by Llamas, with the design and engineering know-how, and we become the forefront in licensing of this technology. And I'm glad to just indicate that we have about 10 units licensed so far, and 6 since 2018. The point I want to emphasize here is the industry is going from a refinery making the gasoline from FCC into producing a very large amount of the light olefins, such as propylene, ethylene, and butylenes, as well as high aromatic naphtha that is important for aromatic complex. So we are glad to be part of this, and India is growing, as Mr. Jain indicated. We need a lot of petrochemicals to sustain to the market demand. So that means the INMAX FCC in particular is going to play a very big role in the region for uplifting the bottom of the barrel into the light olefins. There are 3 already operating units in India. The one that you are seeing on the right topmost corner is the world scale 4.17 million metric tons of grassroots INMAX FCC unit, which has been successfully operating for the last 5 years. And this is one of the prominent units in industry that is going to take forward the crude to chemical objective into the light. Then the other option that we have is the SRDC technology for cost-effective FCC retrofits. Like most of the FCCs, either in India or abroad, in particular USA, have got 1 or 2 FCCs in a refinery complex. So in order to move from a refining business from fuels making to the petrochemicals, so the FCC plays very critical role because 50% of the gasoline produced in the world is basically produced by the FCC, fuel catalytic cracking. So therefore, these assets are there. There are 350 plus units on the around the world which are operating. So therefore, in order to move a refinery from fuel, that is gasoline mode, to the petrochemical mode, is an important aspect to have something that can retrofit into the existing FCC to make it light olefins. Like the process is called single regenerated dual catalyst. What it does is, it is attached to the existing FCC with the 2 tie-in points, and the catalyst coming from the regenerator with some GSM-5 is taken into the system. You concentrate the GSM-5, making the suitable catalyst for each reactor that you have. Like the primary reactor is mainly defined for processing the heavy feeds, converting into gasoline. The second reactor, which is SRDC reactor, is one that converts the naphtha range material or gasoline into the light olefins and BTX-rich naphtha. So the process innovation is such that it is separating the additive and catalyst functionalities between the SRDC reactor and the FCC riser. So that means it is going to provide a superior conversion of the bottoms without sacrificing the catalyst function, which is required for heavy molecule cracking in the primary riser. In the secondary riser, which is SRDC riser, where the GSM-5 is the primary catalyst there, and that is concentrated there to enhance the product yield and selectivity from the SRDC, which is processing gasoline or naphtha as the recycle from the primary FCC. So this enables us to optimize the reaction zones to deliver the superior yields and the product quality. And this is a mission that will minimize the gasoline and maximize the light olefins BTX rich naphtha stream. So the other aspect that Llamas has been working for several years now is the crude to chemicals, TC2C. It is basically a partnership along with Saudi Aramco and CLG, our own joint venture. The focus was developing, commercializing, and marketing the innovative crude to chemical technologies using the hydrogen addition as the platform here. And the combination involves hydroprocessing by CLG and ethylene cracker technology by Llamas, and the TC2C technology, proprietary one, by Aramco. So the objective is again to produce the high value chemicals by minimizing the operating and capital costs, at the same time considering the crude conditioning with a simplified configuration with a tailored catalyst and steam cracking integration. This kind of configurations have been implemented, and we are continuing to develop more and more to make it more cost effective. And this is going to play a big role in that endeavor. Before I get to the conclusion side of it, Llamas is responding to these needs through the innovative solutions for converting the crude into the petrochemicals, and driving solutions to convert residues to chemicals is a challenging that we always have been working on. And we are supported by 4 R&D centers around the world and excellency centers as well. And there are new configurations to provide improved yields, and the low cost and high chemical yields are achieved through like the things that I mentioned: carbon rejection and hydrogen addition. The TC2C is one of the hydrogen addition options, and the expanding the conventional technology applications into the new, as I told, SRDC is one of them. Is shifting the gasoline to the light olefins and BTX is also a prominent research that we took up. Now we have commercialized the technology to one of the leading US refiners, who is a fuel focused as of now, and is moving into a large scale petrochemical complexes. And the hydrocracking is a challenging, challenging feedstocks and selective shifts can be made using the hydrocracking. And as you saw the slides, some I highlighted, residue upgrading is the key aspect that needs to be taken into account. And integrating the refining and petrochemicals involves mainly making the feed to the FCC and the steam crackers. Definitely, pyrolysis is a byproduct from the steam cracker that needs to be seen. How can it be used in the refineries to upgrade into valuable products? And hydrogen sourcing and utility optimization is something that is very important for profitable solutions. The Llamas is uniquely capable of supporting oil refinery for crude to chemical applications, because Llamas is world leading refining and petrochemical technology licensor, focused on advancing technologies for the future market requirements. Experience, know-how on shifting the transportation fuels to the chemicals has been our goal of research and development for several years. Now we are already on the way to support you with innovative solutions to maximize the chemical yields cost effectively for making the refiners a profitable petrochemical integration. In summary, it is very important to refocus the fuel-centric refinery integration into chemicals because of the declining demand for the fuels that is affecting the refinery profitability and sustainability. As India on a growth path with more than 250 MMTPA crude refining capacity, it is very, very important to consider these options. Again, as Mr. Jain in the beginning highlighted very clearly, that you need one cracker for next 10 years to sustain the requirements. It is not only the cracker, it is also the FCC that is going to play a big role in India, because each refiner has got at least one FCC unit. Okay, and there are new FCCs that have been considered by IOCL and other companies are all light olefin centered, which is the right direction to move into the petrochemical scenario. And definitely, as I just mentioned, crude to chemical projects need special attention, because it is important to understand deeply the molecules now and not the range of the products in the distillation now. So that will help us to better understand and see what is the optimal solution that a refiner needs. So it requires kind of a careful analysis of the various aspects of refinery for finding an optimal solution. Therefore, Llamas is available for supporting that kind of activities. And Llamas has pioneered advancing these technologies for future requirement of converting the refineries into chemical hubs. And we are confidently saying that we are fully geared to support you in your endeavors. And thank you for your attention. I'll be glad to take any questions when the moderators want. And thank you.
So questions we can address at the end of the session. So all questions can be addressed by the panelists.
Sure.
We now move forward to Mr. JP Soni, Head of Process and System Design for Green Hydrogen.
Yeah, thank you very much. And good evening from my side to all who are participating in the exhibition and also to my co-panelists. Just let me share my screen. Are you able to see my screen?
Yes.
Yes.
Okay.
Just
So
go
good
to
evening.
slideshow.
Yeah, I had made the slideshow already. Just give me a second. Yeah. Is it okay now?
Yes, sir.
Okay. Okay. So good evening once again, and I will start my presentation with the note that as the winters is already setting in and we are going towards the summer in India, I am sure we need a lot of energy to cool ourselves off. And the rise in temperature, I am sure, is not only due to the change in the season or the change in the let's say winter months, but also due to various other reasons by which the let's say climates are changing, like global warming. See, all of us are needing huge amount of energy to cater all our demands, and for centuries the mankind is using fossil fuel to meet the demand of energy. And it is a known fact that due to burning of all these fossil fuel are causing the let's say greenhouse gases emissions, and ultimately resulting into the global warming and the climate change worldwide. I am happy that all over the world, including our country, are taking a lot of steps to let's say minimize the negative impacts by the studies which are made in these directions. Considering this, on one hand, we have, let's say, a big decline in the fossil fuel, but also there's a huge increase in the let's say population. And there is a study which shows that the population will grow to 8.5 billion by 2030. I'm sure that we will need a lot of things, or a lot of sustainable solution to meet the requirement of all this huge population growth, in terms of whether in terms of food and water, whether in terms of energy, or keeping ourselves in the cool, livable place, and also give us the clean, breathable air. I will take you through one of the topic which is quite important, as also mentioned by Mr. Jain, regarding the green hydrogen, and I will take you through a journey how green hydrogen can help in sustaining some of these topic in a sustainable way. As we all know, the awareness which has increased in the direction of the knowing the negative impact of the issues related to, let's say, fossil fuel or global warming, that has forced the think tanks to let's say, decide on the alternatives, and the alternatives which was found as a renewable energy. And there is a tremendous growth we have seen in the last few decades in the let's say in the area of the alternative or renewable energy. There were a lot of motivation to reach that. First of all, there is a huge availability of these renewables. They are inexhaustible, like solar energy or the wind energy. They are quite environmental friendly because they are not generating any kind of emission. and more importantly, that can give clear, let's say, independence from the oil and gas prices. And most importantly, this can be also produced in situ, or where the demand of energy is there. There is a push from the worldwide governments regarding the, let's say, in the form of taxes or in the form of policy to motivate the use of this renewable energy. However, the, let's say, what we have seen in the past, a lot of efforts had been done to let's say make the renewable energy more efficient, more cheaper day by day. But all the efforts have gone into the, let's say, converting this renewable energy in the form of electricity, or at the most use in the power for the transport. But if you see the chart which I have displayed on the left, the CO2 which is generated is not only because of the electricity and heat, but also the industrial sector plays also a big role in generating CO2 by, let's say, processing various chemicals and forming the emitted gases. I am sure the transition towards this curbing or helping the carbon emission through this industrial sector will also help us to achieve the, let's say, sustainable solution, and reduce the impact of this, let's say, environment which we are talking right now. How we can achieve that? As we know, there is a huge, let's say, generation of the renewable energy, whether it in the form of wind, or whether in the form of solar. And this renewable energy, there is still a limitation. The limitation is this renewable energy is cyclic, and let's say it has a limitation in the transportation, and also very much limited in terms of the storage capabilities. So there is definitely a need to convert this energy, until unless we get some disruptive technology like transmission via wireless transmission, like our telephones or mobile. It is the challenge still. So one of such solution is the hydrogen. See, the energy which is produced by this, the power which is produced by this renewable energy can be easily converted in the form of hydrogen by electrolyzing water into hydrogen and oxygen. Since this hydrogen which is produced by the renewable energy, and there is no carbon, let's say, source involved, this can be easily termed as green hydrogen. And this green hydrogen can green hydrogen can play a very crucial role to decarbonize the whole industry sector by, let's say, and also enhance the carbon protection effort, climate protection efforts, which we are all aiming. Just to give you analysis, if we produce a green hydrogen via this water electrolysis method, we can save roughly 9 tons of CO2 per ton of green hydrogen which is produced. And the benefits are already I had explained in my talk. So today, it is not the hydrogen is not a new chemical for the industry. Hydrogen is used widely in various forms. But today, whatever hydrogen is produced is in the form of gray. Why gray? Because it is generated traditionally by reforming of, let's say, the fossil fuel like natural gas or oil, mainly. And in let's say, in various industry which is going, in terms of percentage, if we see, almost 45% goes as a production of ammonia, this hydrogen. It goes to methanol to certain percentage, and to the large extent refining processes, this hydrogen is used widely. So there are a lot of drivers to convert this gray hydrogen towards the green hydrogen. Some of them I have listed on my slide on the right, that as we all know, the cost of renewable is going down and down. Earlier it was very expensive, but thanks to the various efforts that it is going down. So it is making the production of hydrogen via the electrolysis cheaper, or let's say closer to the refining, to the reforming process. Every year we see there are more than hundreds of gigawatt electricity which is produced via the renewable energy source. So this can be definitely utilized to convert into green hydrogen. And of course, there are various national and international strategies are conducive to let's say help in the direction of production of this green hydrogen. And the best part is it can be stored and transported easily. Just to depict my let's say statement, all the electricity which is produced by let's say renewable source can be converted via electrolysis to hydrogen. And when you store hydrogen, we can convert that let's say whenever there is a demand or the peak demand coming in absence of this renewable source of energy, we can convert it back to the electricity by simply adding a fuel cell. So this is one route which can act. But not only that, this hydrogen can go as an energy source directly towards the, let's say, existing gas grids, which are very commonly used in the western part of the world. It is possible to use this hydrogen directly as a transportation substitute. Like there are a lot of let's say experiments or trials going on with the hydrogen run vehicles. So this also is one possibility. But apart from that, in the industry, it can go directly to the let's say as a substitute to, let's say, like steel production company, where you need energy, or refining, or the cement industries and all. And also it can produce a host of chemicals, which I will just come to in my subsequent slides, to let's say make a value chain. And as explained in the opening remark by Mr. Jain, that in India also the government is taking a lot of initiative to let's say facilitate this green hydrogen. In worldwide, this hydrogen can definitely act as a integration or the integrator to the let's say renewable power to the end user, basically either in the form of direct consumption, or in the form of various chemical let's say production. And the let's say the supports which is coming from the various government agencies definitely will make this possible in terms of utilizing this green hydrogen, I'm sure. In this slide, although it is, let's say, slightly less readable, I will say, but this is just to depict the whole value chain by the hydrogen, what all we can do. Just to explain in brief that as this is the renewable energy source, we can produce hydrogen either centrally, like in the areas of where abundant renewable energy is there, or in situ of the various chemical complexes. This hydrogen can be supplied for the processing to the various industry. Interestingly, this can also let's say combined along with the CO2 which is produced by various carbon or CO2 emitting industries like steel industry or cement industry, and this CO2 can be combined with this green hydrogen, and a lot of value added products can be generated. Some of this product I will explain in my subsequent slide. But this hydrogen, and apart from going to this chemical value chain, also can be sent to the direct consumer or converted back as electricity via fuel cell. One such a good example is to produce green methanol. How green methanol we can produce through the water electrolysis the hydrogen. This hydrogen can be combined with the CO2, which is emitted from the industry, which I just explained as an example, like cement or the steel industry. And we can synthesize this to let's say form methanol, which is traditionally produced via reforming of the fossil fuel. And this methanol can act as a source of a green fuel after, let's say, directly or after processing to various downstream product. The best example is to produce ammonia. Today in India, we are importing huge amount of ammonia to meet our fertilizer demand actually. Or it is produced within India by, let's say, reforming of fossil fuel, natural gas. So we can produce, as I said, hydrogen via, let's say, water electrolysis with the help of renewable energy. We can combine with the nitrogen coming out of the air directly instead of the natural gas reforming, and we can produce synthesized ammonia, which is let's say green because it has no carbon intake or no carbon utilization and no CO2 emission. So this green ammonia can definitely be combined with the downstream to make downstream fertilizer like urea or nitrates, various nitrates to meet the demand of the agricultural sector, and can definitely help in let's say decarbonization of this particular industry. Just to give you the analogy is we can produce about 100 tons per day of ammonia by 40 megawatt of electricity, which is which is generated from the renewable energy. Coming to the various technology of producing hydrogen or green hydrogen through water electrolysis, there are three major technologies available worldwide. First is this alkaline water electrolysis. This alkaline water electrolysis is working with the principle of circulating alkaline water to the cell, which is separated by a membrane. So you separate hydrogen and oxygen into different compartments, and the let's say the alkaline water which is there is circulated back to the cells after enriching. Similarly, there is another technology which is called Proton Exchange Membrane or PEM technology. It acts as I mean, it splits the water through passing through the catalytic conductive solid polymer, let's say, and then it is splitting into the water directly to hydrogen and oxygen. There is a third technology which is splitting water in the form of steam. So the steam is passed through the catalytic converter. So high temperature electrolysis happens here, and we get hydrogen and oxygen. So there are various these three major technologies are let's say different in terms of handling the electrolyte, the cell design, and the separation of ions in the form of oxygen and hydrogen, how it is done. So this is how it is different. So just to give you the example of one of the process is ThyssenKrupp, let's say, technology, where ThyssenKrupp Uday Chlorine Engineers has developed based on the wide experience of world-leading technology of chloralkali, where the chlorine and hydrogen along with the caustic soda is produced through the electrolysis of NaCl brine. And based on that experience, we have developed the let's say module for producing this alkaline water electrolysis to generate hydrogen. This is the 20 megawatt module. So in one module we can generate, we can utilize 20 megawatt and produce about 4,000 cubic meter of hydrogen. These cells are quite large, close to 3 square meter in size. So it can be, let's say, we need almost lesser amount of cell element compared to the smaller electrolyzer. Just to give you some more brief features about this electrolyzer is Like it consumes about 4.3 kilowatt hour per NM cube of hydrogen production. And the hydrogen which is generated in this, let's say, electrolysis is quite high purity, 99.95% purity, which can be further processed, let's say, based on the need to 3 digits of decimal by deoxo unit, actually. This is very reliable technology which has the life based on the experience about chloralkali is more than 30 years. And this complete module comes as skid mounted to so that it can be installed directly at site. And the most important is for any such electrolysis, when we are utilizing along with the renewable energy, is the let's say fluctuating or the flexibility in the operation. So the demand, the production, when it is varying from 0% to 100%, this electrolyzers also can be operated from 0% to 100% of electricity load easily. And these are all very scalable, I will say. So just to show you, let's say, or the layout of or the picture. So the cells which are stacked as a module can be, let's say, expanded in this direction. So if we want to add in future the enhancement in the capacity, it can be easily expanded, and the downstream which are connected along with it also can be easily expanded. So scalability gives the economy. So 20 megawatt can be easily expandable to built to 2 gigawatt level also. So not an issue. So this were the technology part, and just to give you some real life example, there are a lot of efforts which are being put in the Europe, and one of such example is in Germany, where ThyssenKrupp had installed this 2 megawatt module in one of the steel plant as a demonstration, along with the let's say partnership with even the government. So this was a 2 megawatt module which was producing hydrogen by water electrolysis. And this 2 megawatt, the hydrogen which is produced was, let's say, combined along with the gas, synthesis gas, which was coming out from the steel mill. And this is used to produce methanol and ammonia. Of course, this was a small scale because it was a demonstration plant, but it was already started up and commissioned in Germany. And based on the success of this, now in Germany has announced also one big project in Germany in Hamburg area, where which will be, let's say, installed in 2 phases, where the water is, I mean, the hydrogen is produced by electrolysis utilizing the wind energy, and this hydrogen, along with the emission from the nearby cement industry, will be combined to form methanol, and this methanol is, let's say, further processed to make the aviation fuel and also the various other fuel for the energy demands, actually. So this project is already on with the various agencies involved, along with the government of Germany also. To summarize my presentation, yes, we are all, let's say, aware, and a lot of efforts are being put to mitigate the global warming. But let's say this renewables today is, let's say, going in the form of electricity, and there is a lot of potential to tap this opportunity and utilize of these efforts further, increase these efforts furthermore by utilizing the green hydrogen. The green hydrogen, which is traditionally considered as gray and also associated with high carbon emission, can be produced by renewable energy, and I am sure this can be completely decarbonized. Not only the production itself, but also it can decarbonize the downstream industry in the form of producing the various value chain chemical. This is easily storable and easily transportable, as I demonstrated. ThyssenKrupp is front runner in the technology already for the production of green hydrogen. Also, not only green hydrogen, but also for the downstream chemicals like urea, like ammonia and methanol. So we can help in the industry sector. So thank you very much for listening.
Thank you, Mr. Soni. We now have our next speaker, Mr. Marvin Petit-Homme, Global Product Manager Residuals IPCO, presenting on forming and handling of carbon-rich residue streams from bottom to the barrel upgrading processes. Over to Mr. Petit-Homme.
Good evening. My name is Marvin Petit-Homme, Global Sales Manager for IPCO for residual processes. On behalf of IPCO Global and IPCO in India, we thank you for giving us this opportunity to present our company and our technology to the group. But before we get started on the technology, I would like to just say a few words on IPCO, on who we are. IPCO is relatively a new name, but our past, we were formerly Sandvik Process Systems, part of the Sandvik Group, the industrial Swedish company, for well over 140 years. We were divested in 2017 to the Wallenberg Group, Foundation Asset Management, which is a large Swedish multinational industrial group that has controlling interest in a number of high-value multinational Swedish companies, including ABB, AstraZeneca on the banking side, to SSAB, and also to Investor AB. So we are glad to be part of this group, a much bigger group, and we have presence in 35 countries. And as I mentioned earlier, we have a large presence in India, where our office is based in Pune. As Mr. Rama had mentioned in his presentation, what we see and where we are in terms of our development in this bottom of the barrel upgrading technologies, we're seeing a lot of strong incentives, as well as Mr. Rama presented in his presentation, for refiners to really strengthen their link to the petrochemical market in order to generate higher margins through higher valuable products. And some of the incentive drivers are the same drivers that were mentioned in the previous presentation, where the lower demand of transportation fuels, which also existed prior to the global pandemic, but has been actually accelerated by the global pandemic. So that definitely is one driver that we're seeing in the increased demand for projects. In addition, the lower projected future demand of transportation fuels as a result of the electrification of automobiles and light transport vehicles. And obviously this, as the IHS presentation pointed out, this driver is basically regional or geographical, because some regions are more dependent on diesel and transportation fuels than others. And what we're seeing in most of the Western countries, we do see a concerted effort by the global automobile industry to actually move towards electrification of vehicles. Another incentive and driver is really the global legislation from governmental bodies for clean fuel directives, such as IMO 2020. Thus, all of these drivers, it's leading refiners to one area. That area is to strengthen their link with petrochemical market, because the petrochemical market has proven to be more sustainable and more resilient to crisis. And the true link for refiners to link to the petchem market is really creating value in the vacuum residue stream through residue upgrading. A few words, IPCO technology. IPCO is not a licensor of residue upgrading technologies, but what we do, we work with some of the leading technology licensors, such as CLG, Lummus Technology, KBR, Oxon, and UOP, to incorporate IPCO's core technology into their process licenses. The core technology that IPCO offers, it enables the licensors to manage the asphaltene pitch stream from the various bottom of the barrel upgrading processes. What IPCO offers a solidification system to convert the liquid pitch stream from the various BOB processes into a solid fuel for combustion applications. Typically, where we get involved, our core scope of supply ends up being this solidification unit, where the feed to the solidification unit comes from primarily a solvent deasphalting unit. As you recall from Mr. Rama's presentation and one of his slides, he mentioned that solvent deasphalting is a primary tool that is actually used in a number of the bottom of the barrel schemes. So where IPCO comes in, we basically take the pitch stream from the solvent deasphalt and manage it. We bring it into our battery limit, into our process, solidify it from the liquid into a free-flowing form or a random size form. And this solid pitch is now basically feed to either a CFB boiler or to a gasifier. In the boiler, most of our customers are actually using it to provide, to generate electricity. And for gasification, they're using it to actually generate syngas or hydrogen. So what does IPCO really offer when we talk about these solidification technologies? IPCO offers two distinct technologies to aid our customers into converting the solid pitch from the various bottom of the barrel processes into a solid form. The first technology that IPCO offers is what we call our double belt technology. What the double belt technology is, it is what I like to refer to as a dynamic heat exchanger, where we actually take the liquid pitch from the solvent deasphalting unit. It is pumped through via jacketed piping through a positive displacement gear pump, and from the gear pump through jacketed piping into the heart of our system. Our system is actually made up of a lower conveyor. This lower conveyor is cooled by cooling water on the underside, and an upper conveyor, which is also cooled by cooling water on the upper side. In between the two conveyors, what's being driven is a metal stainless steel belt. The belt is usually 1.5 to 2 meters wide, roughly 1 millimeter in thickness, and is welded continuous throughout the conveyor. So as the pitch is pumped through the jacketed piping, it goes through a distribution manifold onto the lower belt. And with this particular process, a sheet of pitch, which is approximately 3 to 4 millimeters thick, roughly 1.5 to 2 meters wide, the width of the belt, is actually casted on the actual belt. And the pitch in the molten phase, usually around, say, 275 to 300 degrees Celsius, is driven by a lower belt. And as it travels through the belt, it begins to cool on the underside. And let me remind you, there is no direct contact between the actual pitch material and the cooling water, because this thin belt, as I explained, serves as the heat transfer media. So as the pitch travels down the length of the belt, it is cooled from both sides. So the heat from the molten pitch is transferred from the pitch to the steel belt, upper and lower, and into the cooling water. The cooling water drains by gravity into a pit or a sump tank, goes through a centrifugal pump, through the tower or heat exchanger, and gets recycled back in a closed loop fashion, such that there is no consumption of cooling water, just a small amount of makeup water due to losses and evaporation. So as the pitch moves down the length of the belt, it solidifies into a free-flowing form and a solid form, and is discharged off the end of the belt. Is discharged off the end of the belt and goes into what we call a product breaker to actually break this sheet that is 1.5 to 2 meters wide into random sized particles that are about 25 by 25 millimeters. And typically some of the other services, when you take a look at this process scheme, obviously the pitch at 300 degrees Celsius is coming onto the belt, and there will be some pitch vapor, some exhaust that's taken from the feed end of the unit, exhausted, and goes through what we call a carbon canister filter. And the purpose of a carbon canister filter is really to remove odor before the exhaust is vented to the atmosphere. This filter contains what we call a demister section to remove any moisture before the exhaust is actually sent to the actual carbon filters, because that moisture would actually derate the carbon elements. And that's why we have the demister. That from the carbon filters, it goes into the atmosphere and vented primarily, as I mentioned, for odor. Globally, I can tell the group that globally there are approximately 2 full-scale plants in operation that are using this technology. One plant is in Europe. The other plant is in China, and we'll go through that as a reference case later on in the presentation. And in addition to those 2 plants, there are 2 other plants that are in construction right now, and startup is slated towards the end of this year for one and next year for the other. And all these plants are looking at taking this solid pitch material to actually either burn it in a CFB or for a gasifier feed. Give you a more look at a 3D model of what this machine actually looks like. This machine is typically, as I mentioned, 1.5 to 2 meters wide, roughly about 40 meters, 45 meters long. And this is a single train. And a single train will do roughly about 250 to 400 metric tons per day. As with the previous presentation, these units are very modular, so they are scalable for other capacities, or increased capacities. 2, 3, 4, 5 different trains can be added to reach greater capacities required. As I mentioned earlier, the typical size of the pitch is 25 to 50 millimeters, 3 to 4 millimeters thick, with a bulk density of 600 to 700 kilograms per cubic meter. And one of the things that we'll take a look at later is really the comparison of this pitch product to, say, Coke, for example. When you take a look at burning Coke, the caloric value for burning pitch is much higher than Coke. So this technology, in some instances, where appropriate, it can actually be used to actually replace coking, meaning the combination of pitch solidification plus solvent deasphalting is a reliable combination that can be used to actually replace coking. And we'll go into the reasons why later on. As I mentioned earlier, IPCO has 2 technologies. The second technology is very similar in that it is based on utilizing a stainless steel belt, as I said earlier, dynamic heat exchanger, to actually solidify a product. Like the flaking technology, basically the pastillation technology starts with upstream equipment. You'll have product in a molten tank, and it is pumped through jacketed piping via a positive displacement gear pump, through filters, but into a portioning system. The difference between the flaking process and the pastillation process is that we're utilizing a different feed device. Instead of putting down a sheet on the actual belt, we're portioning out through a rotary depositor individual pastilles or pellets onto the moving stainless steel belt. As the pastilles travel down the belt, they solidify and cool in the same manner as the previous process. And the pastilles travel down the length of the belt, and they fall into the packaging system or material handling system. Again, the biggest difference between the pastillation technology is that we are producing a free-flowing particle of a specific size, typically between a diameter of 5 to 8 millimeters in diameter, roughly about, say, 2 to 4 millimeters in height. So this is a very consistent size particle with a higher bulk density than the flake application that we previously discussed. And as I previously discussed, the cooling water management is basically handled in the same way. It is a closed loop system where there is no water consumption, just a small amount of water for actually makeup. So if we take a look at a comparison of these two technologies, as I mentioned earlier, this is the flake from the first process that I showed, and this is the pastillation from the second process. As you can clearly see, this is a very more uniform shape, and this is a more, this is less friable, where this is a more random shape, and definitely more friable. Well, one of the biggest differences between these two technologies is where we talk about the capacity. Because the double belt unit, you're cooling the product from both sides and using the maximum surface area on the belt to cool. The capacity typically is roughly 250 to 400 metric tons per day of a machine that's, say, 1.5 meters wide to 40 meters long. And on the same machine, the capacity for the pastillation will be roughly about 50 to 100 metric tons per day. Another key difference, and I won't go into every single point because of limited time, another key area when it comes to handling the pitch from the various bottom of the barrel processes is we have to have a good indication of what the softening point of the pitch is. The softening point really dictates a number of these process variables in terms of what cooling water temperature do we need, what is the required pitch discharge temperature, because as you can imagine, at a higher softening point, you can discharge either product at a higher temperature, so therefore the capacity actually increases. With a lower softening point, what occurs is that you can most likely process it on either process, but we want to make sure we discharge the product at an appropriate temperature so that the material does not soften and agglomerate in the downstream handling equipment. And another difference between the two technologies, when we take a look at, you have greater flexibility to handle various degrees of pitch, and depending on with the flaking process. As you can see, the viscosity range of what you can handle in terms of the flaking process is, say, 500 to 10,000 millipascal seconds versus 3,000 millipascal seconds for the pastillation process. So you definitely do have more flexibility when it comes to the flaking process. Okay. And one other thing that I like to add, when you see the capacity difference, for instance, as you can imagine, there will be a significant OPEX and CAPEX advantage to go with the flaking for a plant because it will take less units or less trains to reach your targeted capacity. As I mentioned earlier, as we talk about crude to chemical processes, IPCO is pleased to be part of the first COTC plant that was in China. And this plant was for Hengli Petrochemical. And with the Hengli Petrochemical process, IPCO actually was receiving the pitch from a solvent deasphalting unit. And the unconverted oil stream was coming to the SDA unit from a ebullited bed reactor. And from the solvent deasphalting unit, the pitch stream was sent to the IPCO solidification, and the DAO was sent to the upstream process. From the IPCO pitch solidification system, the flake was actually sent to a gasifier. that was on site. And if we take a look at the overall project, this is basically a snapshot of the pit solidification area. And what you're seeing here is basically 14 IPCO flaking units to flake roughly somewhere about 25 to 3,000 metric tons per day of pitch. The IPCO scope of supply included 12 plus 2 units, meaning 12 operational, plus 2 standby units, the liquid pitch feeding system, the cooling water system that I explained in the previous slides, the exhaust system, the pitch product breakers, and the pitch solidification conveyors. As you can see, all the plants are installed in the rooftop with an open side building, and each plant basically is parallel to each other with you see the man in the middle of the 2 units. And this plant was basically installed in 2019. It became operational in 2019. Okay. To summarize, the IPCO process, it is not a standalone process. What we're presenting today is basically it's the pitch solidification in combination with a solvent deasphalting unit. And from our perspective and the global projects that we're working on, this combination of pitch solidification plus solvent deasphaltation is really a compelling solution that should be considered for the various residue upgrading schemes. And based on the projects that we are working on and feedback from our partners, one of the reasons why pitch solidification, SDA plus pitch solidification, is an alternative to coking, because for one, with the SDA, you're going to get greater revenue generation as liquid yields are higher as compared to coking. When we take a look at the overall CapEx, especially when a refiner does not have an existing coker on site, to install a coking solution or delayed coking solution, the CapEx is going to be 50% more or 50% less for SDA plus pitch solidification. Thus, you're going to have faster ROI payback as compared to installing a new delayed coking solution. And these numbers are basically from a project that we have worked on, and we have shared these numbers with the actual end user to justify why the end user actually chose to go with this scheme rather than a coking scheme. In addition, what we found that there will be a significant reduction in CO2 emissions for gasification applications when you go with this scheme and you're using the pitch in a gasifier. In addition, the hydrogen content of the pitch with this scheme is 2 times higher in the solidified pitch. Again, it makes it an excellent feed to the gasifier. And one advantage for the refiners who do not have an infrastructure to manage or trade coke, pitch solidification becomes an excellent choice as the pitch is consumed really within the refinery gates. Because as I mentioned, the 4 projects that we're looking at, the 2 projects that are in operation, basically the pitch is being sent to a gasifier or a CFB that is on site within the refinery gates. And the last advantage that we see when we compare the combination of these technologies to coking is that the solidification unit availability or on-stream factor is more favorable, given that repeated need to actually clean the coke drums. Okay, once again, I'd like to say thank you on behalf of IPCO Global and also my colleagues for IPCO India. And I'll definitely be glad to answer any questions during the Q&A period.
Thank you, Marvin. We do have a couple of questions, and these questions are open to the panel. I will start with the first question. What is the future of ethanol in India? And there is a lot of demand for gas plants. So is the future for gas plants in India for the expansion? This is the first question, open to the panel.
What I'm finding, there are two questions in between one question. Can you repeat it?
Okay, so this is what is the future of ethanol in India? And there is a lot of demand for gas plants. So is the future for gas plants in India for the expansion?
Okay, so there are two questions basically. First one is the ethanol. See, each country is trying to decarbonize their energy systems. And ethanol is one of the way, but it's not ethanol, particularly it's the bioethanol, which is important. And of course, now the ethanol also is going to as a transportation fuel. It is getting mixed with the gasoline. And at present, the average mixing is around 6 to 7% in the gasoline pool. But by 2025, the government is coming out that by 2025, 20% ethanol should get mixed. So ethanol, there is a huge demand in the country, and this will keep on increasing till we meet the 20% target in the gasoline. Second question is that the gas. So now this gas which we are talking, this is the biogas. It's not biogas, rather the compressed biogas. So there's around 5,000 CBG plant, compressed biogas plants are supposed to come in India in next 3 years, which will produce roughly 15 million metric ton equivalent compressed biogas, and which will go to the gas grid. So this will also replace it's a replacement for the natural gas, which will utilize, and it will also help to maximize our gas share, which India is aspiring from 6% to 15%. So both ethanol as well as the compressed biogas, both are having great potential in India.
Okay, my next question is for Mrs. Soni.
Yeah.
Which are the commercially proven technologies for producing green hydrogen? And what is the cost per kg for green hydrogen? Please also state assumption on electricity price.
Yeah, if
Electrify price.
yeah. The cost of hydrogen, let's say if we convert in terms of electricity, I had already stated in my presentation, it consumes roughly 4.3 kilowatt hour per ton of per nm cube of hydrogen produced. So let's say if based on the power price in that particular location, it can be easily calculated.
Next question is, how much water?
Now what we are talking is the hydrogen production cost. Okay, now in India, because we are sponsoring many hydrogen projects in the country, with now this renewable power cost has come down less than 2 rupees. So if at the same place, if the hydrogen is produced from this green power, the cost of hydrogen production will be around $4 per kg against the fossil hydrogen or the brown hydrogen, which is available at $2 per kg. So this is the production cost, but this is not going to solve the problem alone, because this produced hydrogen has to go ultimately to the consumer point, which is nothing but either it has to go to the power or it has to go to the transport fuel. So the major issue lies after production of power is the storage and the transportation, and then further dispensing into the vehicle. So even at the $4 per kg what the hydrogen is produced, ultimately at present the cost is coming at a dispensing point is around $12 per kg. So the lot of innovation and R&D has to take place, not only in the production, cost has to be reduced, but also the storage and transportation cost need to be reduced. Thank you.
Thank you, Mr. Jain. The next question is, how much water is required per megawatt of electricity or per NM3 of hydrogen, and what is the quality of water that is required?
Last question first. The quality of water which is required is ultra pure, because any impurity in water will deposit on the either membrane which is used in alkaline water electrolysis or in the catalyst which is used in other technologies. So it is higher than the demineralized water which we need. The water which we need for producing hydrogen is exactly as per the stoichiometric. So just to give you some let's say numbers, is roughly 3 tons of water is needed for producing 1 ton of hydrogen. So roughly in that range. So it's pure stoichiometric regression. So, yeah.
And again, this question is for JP sir. The figures that I have are 48 megawatts for 4,000 nm3 per hour hydrogen. Please clarify, with this capital cost, hydrogen from fossil fuel is much cheaper. In addition, for continuous process industry, unless there is a huge storage facility of electricity or the green hydrogen, you cannot get continuous supply during the night. Please elaborate.
Yeah, you are right.
Referring to power generation through solar panel.
Yeah. First is this, the figure which you mentioned, 40 megawatt for 4,000 cubic meter of hydrogen is wrong, because as I stated in my presentation, we need 20 megawatt power for generating 4,000 nm cube per hour of hydrogen. Yes, the cost today is higher, but same as the case in the renewable energy, when we were talking, let's say few years back, the power cost was more than 15 rupees, 12 rupees, and then slowly it has come down to a value which is much lower than, let's say, coal power price value. I am sure the economy of scale will definitely bring down the cost of the hydrogen. And as mentioned by Mr. Jain, if we are able to let's say make a sustainable value chain for the transportation, storage, and also let's say increase the production of this hydrogen, definitely the cost will come down to similar levels as fossil fuel. But the bigger motive is not only the cost comparison between fossil fuel and this hydrogen, but the, let's say, greed to save the environment across. So that also plays a bigger role in my opinion.
Okay, our next question is for Mr. Rama Rao Marri. If O2C is so attractive, why was it not done so far?
So the O2C is already done elsewhere, probably not in India. Like for example, if you just see the South Korea and some part of the US and also the Middle East, there are a lot of projects that are going on. India still needs a lot of gasoline because of the middle class population, and more vehicles are being added every year, as Mr. Jain told. So the gasoline demand in India will still continue because of the population and the demand of the middle class, However, going forward, when we are talking about the crude to chemicals, it is just not a box of the crude coming in and going out. It is a combination of a lot of things that will go in. If you see the India also, like Reliance is one of the examples where the refining and petrochemicals has been integrated from 1990. They are still continuing. Similarly, just take the IOCL and other companies in India recently. Whichever is the FCC, fluid cracking, that came into the project phase, which are several projects going on now. As I told, we have licensed about 6 ultra high olefin FCC units in India that is on the growth path, moving from the crude to the petrochemical arena. It will take time. It is not an overnight story, but things are in pipeline and we are working, we have been implementing. So as Mr. Jain told, like you need one cracker each year in India to cope up with the demand. So therefore, my conclusion here is that it is coming. It will not be overnight. You will not see visibly now probably in India, though you see elsewhere. But it is coming to you. Another example I just wanted to give you is like US. So far, the gasoline produced in the world, 50% of the gasoline is consumed in US with 300 plus million of the population and compared to 190 plus countries. Okay. So whenever there is a fuel destruction requirement that comes, the gasoline, that will basically be more impacted in US to start with. And India with a 1.3 billion population will take longer time to get over from a fuel driven market to the petrochemical driven market. So we are going in a pace and depends on the location and the demand growth scenario and the change in the trend of the fuel to the petrochemicals. So this will come. You will see as the trend follows, you will see next 5 years a significant petrochemical growth in India, like consumption of the olefins per capita will increase. That will also drive the move towards petrochemicals.
Okay. We have time for one last question, and this question is for Mr. Jain. Is the technology to produce ethanol from off gases by Lanza Tech used in India?
Yeah, along with the Lanza Tech, there are two projects which are under implementation, and they will take the refinery of gas, one at Indian Oil and another at the MRPL. And through that gasification route and followed by the fermentation route, ethanol will be produced. We are also pursuing now more projects from the still off gases system. Even those gases also can be converted into ethanol. And a lot of job is going on along with the Lanza Tech in this regard. Thank you.
Thank you, Mr. Jain, for moderating this session on technology interventions. We would also like to thank Mr. Rama Rao Marri and Mr. JP Soni and Mr. Marvin Petit-Homme for joining us this evening for this session. We now end the session. Thank you so much for your time.
Thank you very
Thank you.
much.
Have a good evening. Yeah.
Bye.
Have a good day.
Bye.
Okay, thank you.
Thank you. Bye.